In radiotherapy, the absorbed dose is one of the most important concepts to understand. It refers to the amount of energy imparted by ionizing radiation to a unit mass of tissue, measured in grays. This energy is crucial because it's what destroys cancer cells. But at the same time, we need to limit the dose to healthy tissues to prevent damage. Finding that balance is at the heart of the radiation therapy. When we talk about absorbed dose, we're really talking about energy being transferred from radiation to the tissue. The goal in treatment is to ensure that the energy is concentrated on the tumor while sparing surrounding healthy cells as much as possible. This is why precise measurement and calibration of the absorbed dose is critical in planning and delivering treatment. Now let's introduce Kerma, which stands for Kinetic Energy Released mass. It describes how energy is transferred from photons like X-rays or gamma rays to charged particles such as electrons in a material. For radiotherapy, we often refer to air thermal, which is the energy transferred to air, and we use this as a starting point to estimate how much energy will be deposited in tissue. Air thermal is useful for calibration because it's easier to measure energy transferred in air before it reaches the patient. This helps us predict how much energy the radiation will deposit once it interacts with tissue. From there, we apply correction factors to convert air thermal into an absorbed dose. However, not all the energy transferred ends up as absorbed dose. A portion of the energy might be lost as secondary radiation like bremsstrahlung, which occurs when electrons accelerate and emit X-rays. But most of the energy from photons get deposited locally in the tissue through collision interaction, where electrons knock into atoms, ionizing them and creating more energy deposition. This brings us to collision kerma, the part of kerma that leads directly to the absorbed dose. It's the energy transferred from photons to electrons that is then deposited in the tissue through ionization and excitation. For most biological tissues, the amount of energy lost to radiation, like bremsstrahlung, is small, so collision kerma is very close to the absorbed dose. Understanding this relationship is essential in radiotherapy. When planning a patient's treatment, medical physicists use air thermal to establish a baseline and then convert that into an absorbed dose by taking into account the properties of tissue. This is done using correction factors that consider energy absorption differences between air and tissue. In practice, this understanding helps ensure that patients receive the correct dose of radiation. For instance, when treating a tumor deep inside the body, we need to ensure that enough energy reaches the tumor, but not so much that it harms healthy tissue along the way. By using absorbed dose and kerma measurements, we can optimize treatment plans, focusing radiation on the tumor and minimizing side effects. One real-world example is the use of intensity-modulated radiotherapy, IMRT, a technique that carefully shapes the radiation beams to target the tumor with high precision. The absorbed dose is tailored so that the tumor receives the necessary energy, while the dose to surrounding healthy tissue is minimized. This level of precision would not be possible without a deep understanding of how absorbed dose and Kerma would work together. Another application is in brachytherapy, where radioactive sources are placed directly inside or next to the tumor. The absorbed dose in this case is calculated based on how much energy the radioactive materials will impart directly to the tumor. Again, using Kerma and collision Kerma concepts to ensure the energy is targeted effectively. In summary, understanding the absorbed dose and its relationship to Kerma is essential for delivering safe and effective radiotherapy. By measuring and calibrating air Kerma, applying correction factors, and calculating the absorbed dose, we can precisely control how much energy reaches the tissue, ensuring that we destroy cancer cells while protecting the body's healthy tissues. Thanks for watching. If you found this video helpful, please like, subscribe, and leave any questions in the comments. See you next time.